Okay, so the next topic we're going to cover in our Advanced Chemical Reactions unit is acids and bases. Again, I'm going to kind of go hand in hand with the PowerPoint here, so if you want to have it in front of you, that's fine. It's just going to minimize how much I actually write on this video itself. Basic things you need to know about acids and bases are the differences. I guess biology and then in middle school, you learned that the difference was based on something called the pH scale. Now we're going to get back into that a little bit later, but just to briefly review, when you were in, hopefully, biology, you learned the pH scale ran from 0 to 14 with 7 in the middle, and you learned that acids had a low pH, and you learned that bases had a high pH. And that's probably about as far as you went with it. So today we're going to get a little bit more in depth on the difference between them, their definitions, and a few other things. So let's start with basic definitions. On the PowerPoint you will see there is a very, very long list of characteristics of each one. Talks about acids having a sour taste, which is pretty funny considering last time I checked you're not supposed to taste things in a chemistry lab. But yeah, they react with many metals. They will turn litmus paper red. But the big thing I want you guys to know about acids is that acids generate hydronium ions, H3O+. If you see H3O+, you need to think acid. Other times it's not going to be written like that. It's just going to be written as a hydrogen ion. If you see that, you need to think acid. In truth, these are really the same thing with one difference. If you look carefully between them, H3O+ and H, the difference between them is simply water. So really, these are the things that are created by acids. It's just a matter of am I including the water or am I not including the water. So H3O+, H+, that's an acid. Your bases, as you look at your PowerPoint, bitter taste, slippery feel, big variations in solubility. They turn their litmus paper blue. But the big thing is bases will generate hydroxide ions, OH negative. So if you take away nothing else, you need to remember that hydronium, your H3O+, that comes from an acid, and hydroxide, your OH-, comes from a base. As we continue on through your PowerPoint, you'll see some other differences. I'm going to let you look at those on your own, but I'll give you the 2-second summary. One of the differences is between strong and weak acids, and then strong and weak bases. No matter which one you're talking about, it's really, really, really simple. Strong acids totally fall apart. So whenever you have a strong acid or a strong base, you will see a complete dissociation in water. So you would take NaOH breaking down to sodium and hydroxide. It is a one-way reaction. It totally, completely falls apart and does not go the other direction. A weaker base or a weaker acid, like the examples you see in your notes, will be reversible reactions. They partly dissociate, then they recombine, then they redissociate, then they combine. Dissociate means to fall apart into what it's made of. So strong versus weak, you're going to see a little bit of that. Oops, sorry about that green line. The next definition you see is an Arrhenius acid or base. Again, there's different ways people define acids and bases. So the Arrhenius definition is all about that H3O+. Okay? If you look at the definition on the PowerPoint, your acid forms the H3O+, your bases generate the OH-. It's a pretty outdated definition. Sometimes it's not always true, and that's the problem. Everything with Arrhenius is actually talking about solutions, and so it kind of implies that everything is made with water. Well, that's not always true. Not everything is a solution. You can actually have acids and bases in solid form. So a more updated version of a definition of acid and base is your Bronsted-Lowry and your conjugate. They sort of go hand in hand. Again, read the PowerPoint. It's very, very clear. These are basic definitions, but Bronsted-Lowry and conjugate go together. What you're seeing with the definition is a Bronsted-Lowry acid is something that donates a proton. Okay, so it's a donator. Donate proton. And a proton and an H+ are the exact same thing. A Bronsted-Lowry base is one that accepts them. So when you look at those guys, and you can see the reaction you've got on your PowerPoint, they are actually going to be both reactants. Okay, in fact, let me erase this word conjugate right here, and I'll show you, just in case you don't have the PowerPoint in front of you. When you take ammonia and you combine it with water, what you will end up getting is an ammonium ion and a hydroxide ion. Okay, that's the kind of combination you will get. So when you look at this, what's happened at the beginning here is I went from NH3 to NH4 and H2O to OH. So for H2O to go to OH minus, it had to lose an H. I've lost an H to go from here to here. That means that this is my Bronsted-Lowry acid. My NH3 had to gain an H to become NH4. So my NH3 is my Bronsted-Lowry base. If you add the conjugate definition into it, that's what's on the next slide, your conjugate is talking about the products that are formed from a Bronsted-Lowry acid and a Bronsted-Lowry base. Your acid is what you make once you gain that proton. Your base is what you make once you lose it. So if we go, acid and base, if we go to the same reaction you were just looking at, NH3 plus H2O, it actually should have had 2 arrows in the last slide. This is a very weak reaction. My conjugates, again, are going to be my products. So if I look, again, I went NH3 to NH4. My NH4 had to gain, a proton. So it's going to be my conjugate acid, because in order to be made, I had to add an H to it. My OH had to lose an H to become OH minus, so this is my conjugate base. Again, these are definitions. But while we're on the track of definitions, I'm going to give you an important one. Amphoteric. See, the joys of lower level sciences when you're in biology and when you're in middle school is we teach you it's pretty simple. Stuff's an acid, stuff's a base, or stuff is neutral. That's a lie. Something that is amphoteric can actually act as an acid or a base, and it totally depends on what you combine it with. It's like that person that can be, the good friend or the bad friend. It all depends on who they're hanging out with. That's what an amphoteric substance is. And the number one amphoteric substance, the number one thing that could be an acid or a base is, drum roll please, dun 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 dun, water. Yes, believe it or not, you always learned water is totally neutral. Sort of a lie, not exactly a lie, but sort of a lie. Water can actually be a Bronsted-Lowry acid or a Bronsted-Lowry base. This is a little bit mind-blowing, so hang with me. If I combine 2 water molecules, believe it or not, H2O plus H2O does not make H2O. I know. It should, but it doesn't. Instead, what happens if I combine 2 H2O molecules, my H's start jumping around. And what I get is a hydronium ion and a hydroxide ion. Yes, you're looking at that right. If you put water and water together, you learn that those are neutral. You get acid and base. So in the water bottle that you have in your hand right now, yes, you have H2O, but you also have hydronium and you have hydroxide floating around in there. You have acid within that water. You have base within that water. It is called the self-ionization of water because it ionizes itself. When it combines with itself, it is making 2 different ions. What's nifty is, because this is a reversible reaction, if you look, it's going both ways. The end result here is you end up with equal concentrations of hydronium and hydroxide. When you see brackets like that, they usually refer to concentration. So if you have pure water, absolutely pure water, nothing else in it, it's not that you don't have any acid or any base, it's that you have equal amounts of acid and base. That's what makes it neutral. Equal amounts of acid and base make something neutral. And really, really, really smart people, which obviously is not always us, they actually calculated how much of each one is in pure water. And what they found is that no matter how much water you had, the hydronium ion and the hydroxide ion concentrations, again they're equal, are equal to 1.00 times 10 to the negative 7th moles per liter. That's the concentration of acid and base in your pure water. So we go a step farther, okay? If the two of them are both equal to that, then I want to see what happens if I multiply them together. So if I multiply the concentration of my hydronium times the concentration of my hydroxide, what I got was 1.00 times 10 to the negative 14 molar solution. And that was with pure water. So then scientists said, okay, well that works for water, let's try other stuff. Every single substance they tried, they found that this right here was true. If you took the concentration of acid times the concentration of base, you got 1.0 times 10 to the negative 14. And it sort of makes sense if you think about it. If you look at three different kinds of solutions, okay, acids, neutrals, and bases, just like on your pH scale when you were younger. Acids have lots of H3O plus and just maybe a little bit of that hydroxide. Bases have a lot of hydroxide and just a little bit of that acid stuff. Neutrals have equal amounts of both. So the reason you can multiply them together and get the exact same number every single time is because they end up being proportional. Okay, you still have both present, but when you combine them, you always get this number. It's, believe it or not, the key to something you need to know. So here's the first thing we're going to do with it. I'm going to write it for you again. Remember, holy moly, that was a 3, I promise. Let's start this whole slide over. H3O plus, much better, that concentration times the hydroxide is equal to 1.00, I hate it when I hit the wrong buttons, 1.00 times 10 to the negative 14th. Okay? So here's the first thing you got to be able to do. If I told you that your hydronium acid concentration or hydronium ion concentration was 1.00 times 10 to the negative 2, and I wanted to find out what your OH was, okay, I know you're thinking to yourself, oh my gosh, this is complicated math. No, it's not. All you have to do is look at your exponents, okay? When you multiply things with scientific notation, what you're really doing is adding the exponents. Trust me on this one. So if this one is a negative 2 and then put together is a negative 14, then that means the OH minus has to be 1.00 times 10 to the negative 12. And the reason that's true, 12 plus 2 makes 14. Okay, look at another one. If my hydronium, and this one's not on your PowerPoint, I'm going to be crafty and make one up, is 1.0 times 10 to the negative 6. And I want to know my OH, okay, it's the same thing. You just have to look at the exponents. So as I look at that exponent, that one's a 6, they have to add up to be 14, so my OH must be 1.00 times 10 to the negative 8. And again, that's because 8 plus 6 equals 14. So as you're going through all of this, you're thinking to yourself, okay, this is way too much number. You're not the only one that feels that way. 1909, this guy named Soren Sorensen, you can't make that up, that was his name, got really, really sick and tired of looking at all these exponents. He's like, I don't want to look at these exponents, it's annoying, I don't want to write 1.0 times 10 to the something, can we just have a number? And he created the pH scale that we were talking about earlier. The pH scale is a logarithmic scale. Now, don't start panicking on me and thinking, but I don't understand logarithms. I don't remember that stuff. It's going to be fine. Okay, the pH scale is all about logarithms. We are doing log base 10. So all that stuff you learned in math, forget it for a second. What a logarithm is the power to which 10 must be raised to in order to equal a certain number. Okay, so if I'm saying 10 to what number is 100, okay, you might be able to look at that and say, well, that's easy. 10 squared is equal 100. Well, what you are really asking in this question right here is you are asking the log of 100. Okay, the log of 100 is the exact same thing as saying 10 to what power is equal to 100. So if I said the log of 0.001, I'm asking 10 to what power is equal to 0.001. That's all a logarithm is. That's it. Now, when they're ones and zeros, there's a trick. This one, by the way, is -3. The trick to doing this, if it's a log base 10, and if all you have is ones and zeros like this, is to just count the zeros. Look, 10 squared is 100. So if I say, what's the log of 100? There's 2 zeros. The log of 100 is 2. If I say, whoa, ignore that red line. If I say, what's the log of 0.001? Looky, looky, there's 3 zeros, and it's a number less than 1, so it's negative. So if I was being mean and I said, what's the log of 0.0000001? Well, that's not really mean. You would count the zeros, 1, 2, 3, 4, 5, 6, and it would be -6. So that's the basic idea of what logarithms are. So if we go back to Soren Sorenson's pH scale, pH stands for the power of hydrogen. Dun, dun, dun. Seriously, that's what pH stands for, the power of hydrogen. How much hydrogen is in something. And there is a formula that you need to learn. Okay, this is yet another one you are expected to know on your SOL. The pH of a substance is found by taking the negative log, okay, of your hydronium acid concentration. Okay, your hydronium ion concentration. You need to know this formula. So, if a question, there's one on your PowerPoint, what is the pH of an HNO3 solution with a hydronium ion concentration of 0.00010, then when you plug it in, pH is equal to the negative log of that number, 0.00010. And when you calculate it out, okay, you would get the pH is equal to negative 4, because the log of that is -4, and then those two negatives cancel each other out. My pH is 4. Very straightforward. Anytime you're given that hydronium acid concentration, you just plug it in. I don't care what the problem says. If you are given this, bam, it goes right in there. Of course, you know it's not going to be that easy. So sometimes what you will see is instead of giving you that, they will give you molarity. Okay, the example that's on your PowerPoint says you have an H2SO4, you have a sulfuric acid concentration of 0.25 molar. Well, the deal with that is I don't know the acid concentration off the top of my head because it's not given to me in the problem. So there's an extra step you have to do for this. Step 1 is you have to look at how the acid dissociates. This method only works for strong acids. Now, lucky for you, basically you don't have to worry about this as much. You're only going to be given strong acids with molarity. So you don't have to decide is it strong or not. But I'm telling you for future reference, it only works for strong ones. So when I say look at dissociation, we have to decide what does H2SO4 break down to. We know it has to break down into hydrogen because that's the key for an acid is to have that hydrogen. And it has to break down into my sulfate. Okay? So I know that's what happens, but I have to make sure my numbers work. Okay? So I know that if this was an H2, I got to end up with 2 hydrogens and 1 sulfate, and now everything is balanced. So then what I have to do is I have to figure out how many moles of hydronium would be made using the mole ratio. Okay, this right here was an aqueous solution. And if you remember from earlier, H plus in an aqueous solution is the same as hydronium because the only difference between them is the water. So I'm going to use a mole ratio. If I have 0.25 moles of H2SO4, that's what was given to me in my original problem. I know I'm going to put moles of H2SO4 down here. For every mole of H2SO4 that I'm starting with here, I'm making 2 of my hydronium or my H. It's the exact same thing. So I'm going to say how many moles then am I going to make if I only have a quarter. So I'm going to go from moles of sulfuric acid to moles of hydronium. Go to my sort of balanced equation. There's 2 of those. There's 1 of those. And so for every 0.25 moles of H2SO4, I'm getting 0.5 moles of hydronium. Okay, so I've looked at the dissociation of that acid to figure out what's going on. Then, almost there, then I can use the pH formula. Okay, so for my third step, now I can do my pH is equal to the negative log of my acid's concentration. So then I can just kind of plug and chug negative log of my 0.5, and when I put it in my wonderful little calculator, I get a 0.3. Because, oh yes, you were lied to. You were told the pH scale went 0 to 14. For the record, no it doesn't. You can have a negative pH. It is very uncommon, but it's possible. You can have a pH over 14. It's very uncommon, but it's possible. Okay, so as you continue through the notes, you'll notice there's a couple practice problems, or one practice problem dealing with pH from molarity. Try it, and try it without the notes, without the PowerPoint, and then go back and check yourself. It will help you a lot. Okay, so that's the idea with bases, but we're not done yet. Okay, so that's how you find it if it's an acid. We talked about finding an acid with H3O plus and finding an acid's pH if you're given the molarity. But what do we do if it's a base? Okay, if it's a base, you have to go back and remember that your hydronium ion concentration times your hydroxide ion concentration is going to be equal to 1.00 times 10 to the negative 14. That is a huge little nugget to remember. The other way this gets written sometimes, by the way, is that your pH plus your pOH equals 14. pH is your acid concentration, so pOH is your base concentration. In fact, you will have questions on your SOL that say you have a pH of 2, what is your pOH? Those should make you really happy, because literally if the pH is 2, the pOH is 12. If your pH is 6, your pOH is 8. It's literally add the two together to form 14. But let me back up again, get rid of that idea. And let's talk about again, what do we do if we have a base? Okay, so if the question is, what is the pOH of a base if the hydroxide concentration is 2.3 times 10 to the negative 4, it's pretty easy. It's exactly the same thing as pHs of acids. You could find the pOH by taking the negative log of the base concentration. Okay, so you would do exactly the same thing that you did before. Exactly. Piece of cake. You don't really have to go anything crazy. That's all you have to do. So if I calculate this, and let me plug it in first, take the negative log of 2.3 times 10 to the negative 4th, I will get 3.63. Okay, there's those silly lines again, sorry. That is my pOH. So that's when you have to remember that your pH plus your pOH equal 14. Once I find the pOH, I could plug it in here, do simple math, and figure it out. You can also do pOHs from molarity, just like we did before. So if I was asking you the pH of a 0.0136 molar potassium hydroxide solution, you know it's a strong one if I'm giving it to you. Again, it's like it was before. First, I have to figure out how does it dissociate. So when I look at this one, KOH is just going to break down. I got to have my OH because that's what makes it a base. And then the only thing left is my K. When I look back and forth, one of those, one of those, one of those, one of those. So this one's pretty easy. Okay, when I do my mole ratio, just like I did before, what I see is 0.0136 moles of my KOH. That's what I was given. My mole ratio is just going to be a 1-to-1 ratio. So if I look at my moles of OH over my moles of KOH, it's going to be pretty straightforward because my answer is going to be the same. So then when I plug it in, this is what you got to remember. What you just found was your OH. That's the hardest thing with acids and bases, is remembering which one you're talking about. You could not just plug that into your pH formula, even though The original problem asked you for pH. The pH formula can only use acid. So I have to find my pOH by taking the negative log of the hydroxide's concentration. So that would be the negative log of that 0.0136, okay, which would give me a pOH, of 1.87. Then my pH plus my pOH is going to be equal to 14. So when I do my subtraction, my pH is equal to 12.13. It's logical, it makes sense because it's a base. And if a base, it has to be over 7, and if it's an acid, it's got to be below 7. Okay, that is a lot of information. It's a lot. So do your practice problems. They're on the front and the back of the worksheet. Okay, take your time, but go back and review this as you need to. Look at these sample problems. What it really boils down to is you have to make a decision first. Is it an acid or is it a base? Okay, it's the first decision you have to make. If it's an acid, you can use pH is equal to the negative log of H3O plus if you're given the H3O plus. If you're given a molarity, then you have to do the breakdown. Okay, you have to see what it dissociates. Then you have to do the mole ratio to see how many you're getting. And then you can do the negative log of the acid's concentration. If you're given a base, what you're really looking at is the same idea. Okay, you're taking the negative log to find your pOH. Okay, and then you also have to remember that pOH plus pH equals 14. Again, if you're given the molarity, you got to do the dissociation. Oops, that's an arrow, not a plus. Okay, do the dissociation, do the mole ratio, and then take the negative log of the base's concentration, and that's when you may have to use this again and say pOH plus pH equals 14. The biggest things you're going to need for your SOL are that. That is huge on the SOL. And you really need to remember that basic pH scale, that acids have a pH less than 7, bases have a pH over 7, that bases generate hydroxide, that acids generate hydronium. I'm not sure if they'll put a pH calculation with a logarithm on there, but they might. It's been a pretty long video. Go take a break. Enjoy yourselves. Be back for the next one soon.